Okay, so the next speaker is David Mattingly, all about Chetsov, the Finetti, Einstein, Fisher, and the geometry of information.
Both of you said, oh, I know Einstein, the rest, Bout. How do I turn this on? On the top. There we go. Yeah, so this is an interesting talk, a good talk to end the day on, perhaps. And this is a topic that I both love and hate. One, because I will be just like you. I spent my year going just like you. Will try to do this talk saying, no way, that can't be right, and hating one. But at the same time, I'm going to come at this from the notion of a principle that I really dearly love, and I think most of you do as well, and we'll see why I'm talking about this. So just to note, this is done with a bunch of collaborators of mine. This is Per Berglund at UNH, Andy Garaci at Northwestern, Tristan Hopsch at Howard, myself, and then George Minnick at Virginia Tech. Okay, here we go. All right, before I begin, since this is a fest for TED, I just want to give a little recollections. I was a student of TED's around the turn of the millennium. And I started off with just computation, because as you get started as a student, if you know how to code, even if you understand nothing, you can still actually be a little bit useful. And then Stefano arrived and things got a little wild. And we invented Einstein ether theory. We got into the notion of quantum gravity phenomenology and Lorentz violation at a time when the theory got hot. And I remember TED walking around the hall as people were yelling, saying, I wish I did stuff that nobody really cared about. You know, we were worried about getting scooped and stuff. There were competitors and things like this. And it's pretty cool. So thanks, TED, for that. Thanks for helping me find an area. And this is sort of a quantum gravity phenomenology talk. Thanks for helping me find an area that was interesting, that helped shape my career. But also, I'd like to thank TED for making it a place that was good to work. I had a kid in grad school, the first one of 5, and TED provided an environment where I could do all this work and be productive and such, but also raise my family. And so thanks, TED, for that as well. And Steve, you also get a shout out to you as my postdoc advisor. He did the same thing, even though this isn't Steve Fest. So my grad school takeaways from working with TED were be decent to people, be joyous in your science, don't be afraid, it's okay to challenge orthodoxy, and allow yourself to ask deep questions. So let's not be afraid for a second. I'm not going to talk about Lorentz violation. I'm not going to talk about Lorentz violating black holes, although I've done a lot of work. There is interesting stuff. We got radiation, we got first laws, we got new ways to embed charges on black holes without local gauge fields in the bulk. It's kind of neat, but I'm going to ask something totally different, something that's really deep that I've been working on for these last couple of years. And it does relate to one thing that TED had kind of come up with, and we've heard about this before already, this notion of the Einstein equation of state paper that we're all familiar with. And I want to take that a little more broader view of this, that we took the idea of changing the ontology of how we think about physics, and that what we had thought of as real space-time, all right, as in sort of an ontological object, all right, a fundamental thing that we have dynamics of the Einstein equations, and we instead changed it and said it was just a manifestation, it's an effective thing, it's an emergent thing based on something else. In this case, it was information theory in the guise of thermodynamics. And the point of view here is that geometry itself can be derivable and emergent, and the rules of information take ontological precedence. So it's a manifestation of Wheeler's maxim. This is a picture of Ted and Wheeler here. Wheeler's maxim of it from bit. Right? We think that it is complicated and bit is not. Right? So it sort of can emerge from a much simpler kind of theory. This is a notion of this. All right? And this last point is really important for this talk, that we're going to take the idea as a preeminent philosophy that the geometric structures that we see in physics are dynamical. They come from something. Right? This basically is general covariance, but as you will see, I'm really going to concentrate on the dynamical part of general covariance and not the everything is coordinate independent part of general covariance here. So it's really the dynamics of this that I'm going to focus on. All right, so let's think about this idea of it from bit. And in quantum gravity, you're doing this idea that sort of putting the idea that GR is sort of less important than quantum mechanics. That's pretty much standard, right? So TED said that, okay, the geometry comes from something more fundamental. We do this all the time, right? So we change gravity, right? You add more dimensions, okay? You go to supergravity, you modify the structure of add a foliation, whatever you want to do. You mess around with the geometry of gravity to make it satisfy the rules of quantum mechanics. in however you want to do it. We quantize gravity. But we take information theory, as encoded in the rules of quantum mechanics, as much more fundamental. We don't do the opposite. We don't gravitize quantum mechanics. We quantize gravity. And we do a lot of theoretical models in quantum gravity to develop the idea of what should quantum gravity be according to this hierarchy of what's more important. And Scott Aaronson, who's a computer scientist, a quantum computation guy, sort of gave a nice summary of this point of view. It says that basically quantum mechanics is it's not really a theory, as he said. It's the operating system that other physical theories run on as application software, with the exception of general relativity, which hasn't yet successfully been ported to this OS. And there's even a word for taking a physical theory and porting it to this OS to quantize. Okay, so we fit our theories of physics into this operating system that we call quantum mechanics. And besides all the theoretical effort to do this, we do lots of vast effort experimentally to test these structures. So, personal example, Lorentz symmetry violation, standard model extension of Kostelecki and Samuel and others, hundreds of terms. People have spent dozens upon dozens of years. Many people are sort of excruciatingly tightly constrained in all of these. And the latest tables of these constraints on Lorentz symmetry violation, it's 130 pages of tables like this. All right, so it's a big summary of a lot of experimental work. So again, quantum gravity, as we think about it, we do all this effort, and we always say that quantum mechanics is paramount, and we fit gravity into the structure of quantum mechanics. As a note that we'll come back to later, as we do this phenomenology, in general, we give a theoretical principle why some infrared principle should be violated. Direct calculation is often difficult, so we just simply parameterize and test. So I want you also keep that idea in your heads of saying that this is going to eventually be a possible effect of quantum gravity that we should just parameterize and test as well. Okay. All that effort quantizing gravity. I'm going to assume a maximalist approach to this third principle. Every geometric structure in physics comes from somewhere and is dynamical. And the it from bit language, galaxies, all of cosmology, in a sense, is trying to derive it in a dynamical way from some fundamental principles of general relativity in the standard model, some initial universe fluctuations, and then we dynamically evolve very complicated structures. But when you think about bit, on the information side, bit actually has a lot of structure too. There are information metrics. There are statistical manifolds. There's all this structure in information theory. And so the question is, where does that come from? Is that also possible to be made dynamical? Just in the sense that the Minkowski metric from GR was also made dynamical. Right? So, first part of this talk is going to be a little brief background of information theory and Fisher metrics and how we actually determine differences in probability distribution. We'll talk about some of the assumptions, which is where the Chetsov and the Finetti come in, these theorems based on assumptions. We'll talk about how gravity violates some of these assumptions and what possibly we should do to really actually do this and kind of gravitize quantum mechanics. All right. Another way of thinking about this, there's less pictorial, is that just look at semi-classical gravity, and I ask, how many metrics are in this equation? Well, all of us will certainly say, well, the left-hand side is just the Einstein tensor. So the Einstein tensor is a differential operator applied to the space-time metric. Definitely a metric. On the right-hand side, we have essentially the expectation value of an operator on some state. There's a metric in there too. And it manifests itself in what we call the Born rule, which tells us how to actually map states to probabilities. This can be made explicit in the geometric formulation of quantum mechanics. So Ted, there's a picture of you there with the block sphere on your t-shirt. Okay, so here on the right hand, this is just the block sphere. All right, so on the left, we have the usual metric, right? Einstein equation is dynamical, G is a function of the space-time metric, blah, 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 blah. On the right-hand side, let's think about how we actually talk about the inner product for a qubit. Right? So we think about the usual case of what would happen if I want to take the inner product here, the probability amplitude, the overlap between some state psi on the block sphere here with the zero state. All right, it's CP1 is the state here in this case. You define a complex coordinate. There's a Kähler metric here. This FS stands for Fubini-Studi, which we'll get to. And it basically is equivalent to the round metric on the sphere, modulo a prefactor in front. And then the geodesic distance between 2 points on this sphere is given by just integrating along a geodesic between the 2 points. The distance is just the quantum angle theta over 2. And the Born rule then is given by just cosine squared of theta over 2. Gives us the Born rule. So in other words, the Born rule can be reinterpreted as literally, oh, I'm going to integrate along geodesics, at least for the block sphere, I'm going to integrate along geodesics between two states on the block sphere. It is a geometry. Right? But did anyone ever tell you in undergraduate quantum mechanics, well, we think this is true, but we haven't really tested it yet? Oh, they said, here's the Born rule for quantum mechanics. And that was it. There's no context, right? There's no notion here of saying that, well, maybe it's true, there's other theories, et cetera. So in other words, we assume that the Born rule, this metric, all right, on our Hilbert space is totally non-dynamical. It's given to us a priori. It comes from above. I don't know where it comes from. It comes from somewhere, and it's just given to us as fiat. And there's lots of proofs out there trying to prove the Born rule, but all of them actually use something equivalent to an assumption, an additional assumption to quantum mechanics to prove the Born rule. So this talk is all about what happens if we apply the lessons from gravity, the deepest lesson of which is that everything is dynamical. I would argue that's actually the deepest lesson that we learned from general relativity. Embedded in general covariance to information geometry and hence quantum mechanics. We actually do gravitize quantum mechanics. We change the informational structure that's inherent in the Born rule. And there's two questions, well, three actually. But first is this possible and even consistent? That's an interesting question. And then two, how would you actually test this would be the third question. I'll give you just as a starting point, probability theory and quantum mechanics from Hardy's 5 axioms. Talk about probability spaces, some of the information geometry behind this. And then here 4 is where the gravitational obstruction comes in, when we talk about gravity and quantum gravity. And then I'll give you ways to actually say, okay, well, if you weren't going to have this, if you didn't have this, these theorems didn't go through to prove that the Born rule and the corresponding Fubini-Study metric is really the only allowable metric, what might you expect as deviations, and then how you might test them. So again, it's quantum gravity phenomenology in this sense. And then this is the part that I hate because I spend a lot of my time reading different proofs of the Born rule and trying to find exceptions and where the assumptions don't actually hold for gravity. This last part, I'll talk about some of those in a bit. All right, so you have to start somewhere. And the list of ways to derive quantum mechanics, or the assumptions of quantum mechanics, is a long and varied literature. As some of us, Michelle, know, right? It's a very long and varied literature. What I'm going to do is I'm going to start with Lucian Hardy's 5 axioms for quantum mechanics about the turn of the millennium. And he says that, oh, if you have these 5 axioms, then you either have classical probability theory with the first 4, and then you'd also have continuity. Basically, you have continuous transformations between states and stuff, and that moves you into quantum mechanics and quantum probabilities instead. And the question then will become that, does gravity violate any of these axioms? And if so, then the rules of quantum mechanics may differ. I am not going to say in this talk that they're wrong. That's not the point of this talk. All I'm going to argue here is that some of these theoretical ideas that we've taken into account, okay, don't work. Like the proofs fail for gravity. We have this moral idea in front of us that everything should be dynamical, and hence we should test them. That's all I'm going to argue. So please don't take this as I'm arguing here that quantum mechanics is wrong. I'm arguing that there are options that we should consider. Okay. So the axiom that I want to concentrate on, and I can do things with other of the axioms as well, but the axiom one will be the most pedagogically appropriate one, is the following, is that relative frequencies, so how we define probabilities, relative frequencies measured by taking the proportion of times a particular outcome is observed. So you're doing a sequence of measurements on a system. You have some system there, it's composed of particles, they're in an identical state, they've been given the same preparation, and you just go bing, 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 and you grab out outcomes from the system, right? They will tend to the same value, all right, the relative frequency, which we call the probability, for any case where a given measurement is performed on an ensemble of n systems prepared by some given preparation, the limit as n becomes infinite. All right, so that's how we talk about the frequentist approach to defining probability. I will stick with the frequentist approach. This is a phenomenology talk. I have to connect to experiment. Therefore, I will not be talking about cubism, okay, or something where there's actually a Bayesian probability based on priors and assumed priors. We're going to stick to the frequentist approach to probability so I can directly relate it to experiment. So what happens is that when you mathematically sort of define this, is that you need a couple of elements. You need, first off, what's called a probability space. So a probability space, all right, is a space for a single shot measurement is going to be, I'm going to have an outcome, all right? So for example, the set of up and down for a Stern-Gerlach experiment. That's the set of outcomes when I do the measurement. I can get one or the other. You will need a specification of which subsets F of sigma count as events. Call this F set capital F. It satisfies a certain algebra. It's called a sigma algebra. Okay, and what this does, it allows you, it's part of measure theory. It allows you to define a measure for the space. And then you also need then a set of probabilities, some function P, that assigns to each event F sub I a number in 0 or 1 with the sum of the total probabilities acting on the entire space of outcomes equal to 1. I want some version of unitarity. Okay, things need to happen. They can't just vanish. And then you also say the probabilities of disjoint events, adding as usual. To connect this, this is independent of frequentist. It says nothing about frequency here. It's just saying here's a probability space. If you want to connect to experiment, though, you want to actually be able to determine probability distributions to verify a theory, the theoretical prediction. You need frequencies. You need the repetitive notion of experiments. Yes?
Between an outcome and an event.
So basically what happens is it allows for binning. Okay? So basically you can have lots of outcomes. You want to actually call them, and so it allows for a coarse graining and stuff to do, which is why you differentiate the two.
Okay.
Yeah, yes.
But this is the definition of a classical probability.
Yes, I'm just classical probabilities.
Quantum mechanics, what you're talking about?
Yes. Yes, there are still outcomes of measurements. And some of the probabilities all still add to 1. Okay? So the question for quantum mechanics is going to be, for classical mechanics, we have the actual ontological objects be just the probabilities themselves. And for quantum mechanics, we have the probability amplitudes. Okay, but the overall probabilities that you get for a measurement, they still will satisfy this. Okay? To connect to an experiment, you then need this notion of frequency. So you need to say, I'm going to have some infinite sequence of independent, identically distributed repetitions. The outcome of the nth trial is a random variable. It's a variable that takes a value amongst the possible outcomes, taking values in sigma. Then you define the probability by the relative frequencies here, the number of outcomes. Okay? The key thing here is identically distributed repetitions. So in other words, when you do a sample, any good statistician will tell you, you take a sample from a system, great. You take another sample from a system, and the system doesn't change its probability. It doesn't change its distribution when you sample from it. That's why every single one of these samples is supposed to have the same probability map. This is in Hardy's convergence. As you do n periods of time, the relative frequencies will converge to the actual probability of the theory. So this is going to be important, that each sample is independent, it doesn't correlate with past samples, and it's identically distributed. This is what we need to define these types of probability spaces for probability theory. Given a probability, we now have the notion of probability theory. We have the notion of possible probability distributions that you could have on an outcome space on these samples. So in other words, I've kind of given you the sample space and the probability space, but I haven't given you the geometry. So for example, so here, this is now a statistical manifold. So consider all possible probability distributions over some outcome sigma, right? So they satisfy this. This is a statistical manifold, S of sigma, and in general, it's a simplex. So it's sort of a coin, sort of a biased coin. So what are the probabilities that you could have for a biased coin? Well, the easiest one is that it's 50-50. That's what we're all used to. I could have also biased it and said that I will never get heads. That means that, for example, if I had P for heads and 1 minus P for tails, it means that that coin has a P of 0 for heads, right, and 1 for tails. So the space of all possible P's for a biased coin is between 0 and 1. Right? So it's the open interval between 0 and 1. It's a simplex in 1 dimension. If you do it for 3 outcomes rather than 2, you get these types of triangles here. So these are just simplices. So as you go more and more outcomes, you get higher and higher dimension simplices, et cetera. So, all right, now if there's some, this is space of all probabilities here in this simplex, just the possible probability distributions. Now what I'm going to say is that now we want to compare these probability distributions to some model of the world. So I'm going to say there's some theoretical model. It's controlled by some set of parameters theta I, different theta than before for the quantum model, some parameters theta I. And so my probability All right, it's going to be a function of, oh, what outcome I got. So the probability of getting an outcome is going to go to the probability of getting an outcome and possibly these parameters theta. So in other words, these parameters theta, they parameterize different probability distributions that you could have put on the simplex. They parameterize the different options here. And now you can ask, given two probability distributions generated by different values of these parameters theta, how far apart are they? Right? Is there a notion of distance for these types of probability spaces? And the answer is yes. Okay, for any probability in the statistical manifold, the natural notion of distance for the information metric is the Riemannian metric here. It's called the Fisher metric, or the Fisher-Rao metric. Equivalently, this is also possible to understand as the Hessian of the relative entropy between two probability distributions. All right, so it's related to our notions of relative entropy in that case. Okay, so great. Here's a metric. Why is it natural? Why couldn't it be something else? 10 minutes left. Did I start? I will see you outside later. Okay. All right. You're glad we've known each other for 30 years. Okay. So there's a theorem. It's called Chetsov's theorem. It says that this is not only the natural geometry, the natural metric to put on these probability spaces, but it's actually the unique one. It's the only one that you can put on these probability spaces under the notion of what's called sufficient statistics or contraction of Markov morphisms. And basically what this means is the following. Is that say you had some set of outcomes, 1, 2, and 3, and you have some probability distribution on them, and you do some stochastic processing. You have a quantum channel or a classical channel. You have some coarse graining of outcomes. You have some randomized function where you just flip the labels around, et cetera. And what it means is that the metric has to contract into this, that if I do any sort of map like this, I can't magically gain more information, more distinguishability about the probability distributions by doing this map, okay, because information should be lost. So what it says is that if I do this map to get some new probabilities, P prime and Q prime, the distance or distinguishability between these new probability distributions must be less than the original distinguishability. And what this means is that information's lost. Okay, I can't magically take a set of data, do some operation to it that basically sort of randomizes things, and somehow get more distinguishability between two populations than I had before. So this is a data processing inequality, all right? And if you take this, then the Chetsov proved that the Fisher-Rao metric is the unique metric that satisfies this data processing inequality for any possible stochastic map that you can do. It's only this. This is why we think that it is non-dynamical. Right? There is a corresponding quantum mechanical theorem. Yes? The distance computed in this metric. Yes, with the GED computed in this metric, exactly. Okay, so any statistical map you get two new probabilities, P prime, Q prime. Compute the geodesic distance, it's smaller. All right, this is the only metric that does that. There's a corresponding theorem for quantum mechanics that was developed by Petz. And for pure states, for mixed states, you get actually a class, a family of metrics. But for pure state, it also forces the quantum metric to be the Fubini-Studi metric that we talked about before in the Bloch sphere. So there's an equivalent quantum operation where instead of stochastic maps, you're talking about CPTP operators, CPTP maps. So the logic here that we have is that in classical physics, with the frequentist approach that we can connect to experiment, we have the notion that it's IID, independent identically distributed sampling. For our experiment probability spaces, gets you to probability spaces, you get to Chetsov, then you get to the Fisher-Rao metric. Quantum physics, frequentist approach, same thing, IID for our samples, you get to probability spaces, but with quantum, you use Petz and you get to Fubini-Studi. So in other words, in both cases, as long as we have the notion of frequencies for experiment, as long as we have that, oh, when we do the experiment, each time it is independent and identically distributed, and we have data processing inequalities and sufficient statistics, the classical and quantum pure state metrics are unique. There's no dynamics. Irrelevant question. Question. Oh, okay. Great. We should go home. Obviously not, because Stefano hasn't raised his zero card yet. Okay. All right. Here's the problem. So this is the usual IID setup. So we say, I have some system S. Whatever, it's really some measurement process that happens, and it gives me some outcome X1. And I'm going to be, this is an operational, it's phenomenology, it's an experiment. I have to store X1 somehow, right? I have to actually measure X1, stick it in a box in some state, encode it in some quantum state. That state propagates, I keep it. All right, I do the next thing for system S. I get my measurement, I get x2, do it again, I get x3, I go on infinitely. All right, for these measurements, I collect my relative frequencies, I calculate my probabilities, I go to town. Okay. With gravity, this happens. In other words, every time you take a measurement and you store it, you actually have to store it in some physical object, right? You store it in the state of some sort of field. You store it as a counter. And everything type of quantum information that we store will gravitate. The argument here is that, just naively, you can't shield gravity by the equivalence principle. There's no negative masses. Permanent local quantum information would violate boundary unitarity. Right? You'd be storing it and not letting it leak out to the boundary, so it would have no representation there. There'd be no corresponding operator. Or, for Antony, gauge invariant observables in quantum gravity are often dressed. They don't commute. So if you wanted to actually get gauge invariant static quantum information, you'd have to dress it. Right? And so it wouldn't actually commute with the system S. So as a result, each of these gravitate. And the outcome that you get, the order of the outcome that you get, matters. Because if you have some sort of system where energy state 5 records outcome is for recording outcome 5, and energy state 1 is recording for the outcome 1, then whether you get 1 or 5 first matters. Because they will have different time to act gravitationally back on system S. I get outcome 1 first. All right, it will gravitationally modify S to make it S prime, because you can't shield gravity. Then I get outcome 5. It'll gravitationally modify that to get S double prime. Right? Now, I am not arguing here that the effect is large. Okay? This is a purely theoretical argument about why we just can't trust IID, because the physical process of storing information and doing our data processing will gravitate back on every single system that you're actually trying to measure. So the analogy with the early relativity here is the following. In Newtonian and special relativistic physics, observations and dynamics of systems, they occurred in a background space that was non-dynamical. This is either the Newtonian or Galilean relativistic structure for Newtonian physics, or it's special relativity, right, where the background metric is just a Minkowski metric and doesn't actually do anything. In this theory, there were ideal non-gravitating clocks and rods, right? So they're dynamical. They sort of, they'll tick in different rates, right, depending on how fast they're moving, but they don't gravitate at all. And so I can just slop them down on Minkowski space. I can measure whatever I want, wherever I want, to whatever fine detail I want, and none of the clocks and rods are actually going to change the space itself. Great. It's not the real world, but great. Okay? And we are allowed these absolute geometric structures in the terms of the Minkowski metric. And here, what I'm arguing is that in information geometry, observations and information about physical systems is stored and processed in an absolute data processing space that is also non-dynamical. We store things in our elements. We have observations. We take statistics, and we just store them in stuff. And we never actually say that, oh, that act of storage can actually back react on the system at hand. And indeed, when I make that assumption, just as making the assumption of ideal clocks and rods, there are ideal non-gravitating data memories and absolute geometric structures, in this case, the Fisher information metric. Right? So gravity, though, makes any physically realizable local data processing space with permanent memory dynamical and back-reacting. It breaks this IID assumption. It's yes, Steve?
The states that are storing this information must have different energies.
I'm assuming that they're going to be stored in some way that actually generates a distinct gravitational field. Right. So this is things that are stored, right? So they persist for, they're like conserved charges, okay, that will persist for all time, so I can do the frequencies. And so, yes, they will gravitate in different ways back on the system S. I'm happy to argue this point, right? I mean, Giddings and Donnelly had that you can sort of seem to do it locally for quantum information at first order in G. But Don and Ted have stuff in their papers saying that it seems to contradict that you should actually have representations of these things that go all the way out. But yes, I am assuming that for now. Okay, yeah.
Something that like leaves at the state of light.
Oh yeah, right. So in that case, okay, you can put a state of leaves, but so that's all right. So let me Can you hold on to that question for 1 second? I'm going to answer in a second. Okay, yeah, all right. So this is the number 2, effectively here, okay, is that the constant is that there's no size estimation of the effect. All I'm arguing is that the effect happens, all right, but we currently trust quantum mechanics all the way up to the Planck scale. There is no EFT for quantum mechanics, right? I'm simply pointing out that perhaps we shouldn't in quantum gravity. This goes to your question. Can I design experiments where this effect is basically gone? All right, so one way would be to go all the way up to the speed of light and then collect data at asymptotic infinity or something. Absolutely, all right? So presumably, scattering with asymptotic states is a minimal deviation, right? As data stored in infinity would not have much gravitational effect. This is the equivalent of saying, I store it, I send it off, who cares, right? We are not going to see this in accelerators. We probably wouldn't see it in ADS-CFT, where we're dealing with asymptotic states and such, right? So this is really a talk about local experiments that we could do, and could we actually determine the Born rule being true for local quantum gravity experiments. There are other gravitational arguments that would have to get invoked against loopholes that preserve uniqueness, including no signaling, weak gravity conjecture kind of stuff, and entropy bounds. But there's always these weird little gravitational quirks. I'll talk about that afterwards if you want, that kind of come into play for various ways you might try to get around this argument. All right, so great. So maybe there's this loophole, maybe it's not a unique metric, maybe we should think about the dynamics. How would you tell what the corresponding changes would be? You know, maybe, okay, so maybe it's not the Born rule, maybe it's not the Fubini-Studi metric. What would you replace it with? So this is where De Finetti's theorem comes in. And De Finetti had a theorem that said that if you take an infinite sequence of random variables to be exchangeable, i.e. there's a permutation symmetry between the outcomes of each variable, meaning that the joint probability of any finite subsequence is invariant under permutation of indices. So I took a sequence of these random variables and I just swapped them around, okay? And that sequence can be represented as a mixture of IID processes, right? So what this means is that if I have this exchangeability, if I have the idea that, oh, well, x1 and x2 and x3 and 4 in my previous slide here didn't actually gravitate, so it didn't actually matter if I had this exchangeability, then I can get all the way to IID, okay? And if I get all the way to IID, I can then apply Chetsov and get to the uniqueness. But if the storage is in different physical states that gravitate differently, then the permutation symmetry is broken. The system S will react differently depending on which outcome was first. And therefore, one of the ways to kind of get an idea of what might happen is to examine the breaking of this permutation symmetry to determine what are the possibilities under less restrictive symmetries for what the possible modifications to quantum mechanics might be, albeit without size information. So how do we do this? Let's first do it classically. So permutation of a sequence of outcomes implies the IID in a probability space for a single copy measurement. Invariance then under stochastic math leads to the Fisher metric, unique metric via Chetsov's theorem. If you break the permutation symmetry, you say that x1 is not equal to x2, right? Or x2 does not have the same as x1. I can't just swap them in the order of what I measured, right? Then you can actually construct permutations that yield actions on the corresponding single copy space you would have gotten. And what this means is that they are stochastic maps, but they change the state. They change the definition of the state that you're trying to measure on this sort of single copy state. And what this means is that you can actually get more general metrics in this case. So here, for example, is a metric. This metric that I have here on the space is called a weighted Fisher metric. It's not actually the one I'm going to talk about, but it gives a good example. This one, all right, winds up being exchangeable under P1 goes to P2. Right? So if I exchange on the state space, P1 goes to P2, and this metric is symmetric under this, but it's not symmetric under the interchange of P1 to P3 or P2 to 3, P3, et cetera. So it's only invariant under a partial symmetry group. And indeed, we get extra terms. We get extra cross terms in particular here. And these then are the weights that sort of give the symmetry breaking aspect. So W1, W2, and W3 are different. So the point is if I break the exchangeability of the permutation symmetry, you can actually have different types of probability metrics. You can do this quantum mechanically, right? So if you consider a Q-trit, there are 3 possible outcomes upon measurement. There's a quantum version of De Finetti's theorem by these folks here. It came up in cubism, although I'm not going to use it, and which says that if I have a sequence of states that I store with a joint density matrix invariant under swaps, so swaps are just taking it's a product state, I just swap 2 elements of the product state, is a swap operation. All right, then it's actually that joint density matrix can be built from a tensor product of n copies of a single copy density matrix. Right? To that, then you apply Petz's theorem, and you're back to the Born rule. So what this means is that what happens here is that just like in the classical case, the deviation from quantum mechanics when you violate permutation symmetry may manifest in these basis-dependent probability rules. So in other words, this probability rule, this information geometry here, this depends on, this is not an invariant, right? This does not have rotation. Like, it didn't have the symmetries, right? So I can't just rotate this thing and have it be the same metric. So the price you pay for having this type of modification is that the Born rule becomes basis dependent, right? So you can get modifications, you can get changes to it. I shouldn't say the Born rule. The probability rule is a basis dependent probability rule, okay? But with that, then you can get these types of higher order interference terms. You can get the type of cross terms, right, between whatever you between the original, in the quantum mechanics case, the quantum states. So the underline here is that take a basis, associate the basis to an actual measurement device and an actual data storage device that back reacts on the system at hand, right? Then each configuration and environment scenario back reacts and can correspondingly change your probability rule. So what you get in quantum mechanics is the following. Take the qubit, and Raphael Sorkin actually developed a framework for this in 94. So you consider the qubit, all right, just put it in some basis, arbitrary basis. Again, I can just do basis dependence. I don't have to think about the whole state. Take the inner product with some other state phi, okay? Standard quantum mechanics, you have this, right? Given a basis, you could also have defined other rules, right? So the other rules that you would have that could be possible for your information metric are the usual Born rule plus extra corrections. This is actually a quartic correction in these amplitudes, all right? It's a real number. It satisfies certain symmetry properties about the total symmetry property. And then this gamma here is the size of the effect, all right? And this is very experiment dependent. Right? So it's sort of an effect of how you do the experiment. Anyone who thinks about GR should be aghast at this. This is horrible, right? We think about general covariance and diffeomorphism and variance and things are coordinate independent. And here I'm saying, oh my gosh, right? This is a basis dependent thing. So yes, all right, so let me return to that in a second. The Sorkin hierarchy, all right, he did this actually for all of them. He said that, oh, you could have classical probabilities have no I2, all right? So in other words, for A union B of two events, the probability of A union B minus the classical probabilities is 0, all right, for a classical probability, all right? There's no interference term. You can do it then for quantum probabilities. You have, there's I3, all right? So a triple interference term in the probability rule is 0 for quantum mechanics. You can go I4, right? You can develop theories, generalized probability theories where there's an I3 term and not an I4, et cetera. All of them, though, are basis or experiment dependent, and they are non-zero only when support exists on all outcomes. So you only get these types of terms when you actually have support on all the outcome possibilities. So sort of maximally superimposed states. The known experimental limits, all right, that are published, you can probably get more just by looking at the literature or thinking about other experiments a different way, are basically order in 10 to the minus, order in 10 to the 1 and 10 to the 3. So in other words, like the quoted published limits in the current literature on the validation of quantum mechanics is 1 part in 10 to the 3, which is kind of staggering. That's the one, all right? You can generate similar terms to all the Sorkin parameterization. Also, by thinking about the way it works in terms of the geometry is that the correction of the Fubini-Studio metric takes a Finsler characteristic. Okay, so the dynamics would have to be a Finsler form. But the point here is that the metric, right, the Fubini-Studio metric, goes to a metric that's a function of the state, all right, and the state's involved, and also the experiment around it. So it's sort of contextual in a way that quantum mechanics is not. All right, so this notion of this issue of basis dependence. We don't know the dynamics. Right now, what we're actually in is that we're equivalent of Entwerf theory. Does anybody remember what Entwerf theory was? Yeah, a couple of the older folks, right? Okay. Yeah, so we weren't around when the time Entwerf theory was over. We're not that old. All right. So Entwerf theory is one of the halfway houses that Einstein was in. All right. So it basically says that, look, it's not special relativity. The metric's dynamical. I need to construct some field equations for it. So Einstein, in his efforts to find general relativities, he was struggling with holes and all that kind of stuff, said, one of the possibilities is this type of action. You can also write in terms of Christoffel symbols, et cetera. And here's an equation of motion for some dynamical metric, all right? But it's not generally covariant, right? It's coordinate dependent, depends on the basis. And that's the status of where we are right now, is that we don't know what the dynamics are. All we can say is that, oh, some of these theorems about information theory seem to be violated by gravity, strongly violated by gravity. And so the proofs here that this is the only possibility fail. So we're kind of in this Entwerf theory. But there is an experimental signal that would signify not quantum mechanics, but it's a basis-dependent thing. And the way you would see it, we have the proposal for this right now with Andy, who does AMO physics at Northwestern. So basically, there's a phenomenon called a Talbot carpet. This is the carpet here. What you do is you take a laser optics, you put a bunch of photons through a grating, okay? It causes interference patterns. And if you look at the near field interference patterns, you have these incredible kind of repeating patterns that go on spatially. And because it's an n-order interference pattern, and because there's so much data here on the Talbot carpet, it actually winds up being a really sensitive probe to these types of tests of quantum mechanics and these higher order interference patterns. And numerical simulations of this kind of thing with heavy nanoparticles, which we use to sort of maximize the gravitational effect, yield that the Talbot carpets that you would get would change due to the higher order interference, okay? It's an exaggerated picture, it's not this strong. Would change in a way that's actually distinct from the usual decoherence, happening that would also destroy these types of interference patterns.
Gravity affecting this thing.
It's putting constraints on any possible modification of the Born rule. Right. You wouldn't necessarily, right? All I'm saying is, so here's what we do for quantum gravity phenomenology, right? We say that, oh, you take your quantum gravity theory, and I'm not going to say, oh, it violates this particular principle. I have no idea, right? It's like almost impossible to calculate from some of these theories what the actual infrared effect would be. So you say, okay, well, I'm now going to take the qualitative infrared effect. I'm going to parameterize all possible variations from what I think is, the standard model or whatever, and I'm just going to test those coefficients. That's the logic here. So we're saying that I don't know. I can't predict for you what the size of the effect is, but I do know that the limits are 10 to the 1 part 10 to the 3, and I'm going to start saying, can we actually test them phenomenologically? All right, so this can't possibly work. All right, reasons are Gleason. If people know the various theories from quantum information, quantum foundations, we're at 0, right? Yeah, Gleason theorem. It actually assumes non-contextuality, so the basis dependence that I have removes the assumptions of Gleason's theorem. Masani's and Galli, they assume that the usual Hilbert space that we talked about would factorize into a product space. That's not necessarily true in gravity. There are decision theoretic arguments for the Born rule by Deutsch. It also assumes permutation symmetry of payoff values for the decision maker. And then the one you might be most familiar with is this theorem by this set of theorems by Weinberg, Polchinski, and Giesen about no signaling. And that's a statistical argument of basis-dependent probability rules, not one shot. So in other words, what that means is that those experiments tested, I'm going to make a modification of the Born rule that is not dynamical, that doesn't depend on the experiment. And if I do that, absolutely, all those no signaling things work. They say, oh, Alice, it's a basis-dependent probability. Alice has a free choice of basis, so take Alice and Bob in entangled states, send Bob far away. There's lots of states. Alice can now actually measure, right? And she can choose her basis. And because it's a basis-dependent probability, she can actually signal something to Bob. But all of that assumes, okay, that the rule is fixed. And if these modifications are really small, Alice and Bob need a lot of measurements, right? They need a lot of data storage. They need a lot of gravitational back reaction from that data storage, et cetera. And so it kind of evades that proof as well. So we can find assumptions in each of these that evade the proof of this modification. Doesn't mean it's right. But what it does mean is that maybe there's another avenue for quantum gravity phenomenology. That instead of quantizing gravity, maybe we should also think about gravitizing quantum mechanics as well. And if we don't, then we also then have to answer the question, where does the structure of quantum mechanics come from? Right? 5 axioms is still a lot more than 1 for a reductionist. And so those will always sit there at the basis of our theory. The current known limits are surprisingly weak. Current careful analysis of, scattering data, I don't know, whatever, could improve those. And so the proposal that we have right now is just to follow the usual quantum gravity phenomenology approach. We parameterize the possibilities in terms of all these higher order interference terms, and we carefully redo the usual quantum mechanics arguments, looking at those, and we just experimentally test. And with that, I will conclude.
Okay, questions?
Hi, the number 1 part in 10 to the 3 or big seems extremely large. I would have expected that there are so many accuracies.
15 or something, right?
Yeah, there are so many accuracies for reported accuracies for quantum experiments that are way higher than that. How do you reconcile those with this accuracy for the Born rule?
I completely agree, and I suspect that if somebody looked at, for example, fidelities, right, in Qtrit quantum computers and such, they could rapidly improve that.
Okay.
That same as there's that's low-hanging fruit if anyone wants to look, right? But right now the published limit, right, from dedication is 1 part in 10 to the 3.
Okay, where is this published?
What?
Who published this?
Oh, who did this one? This was a triple experiment. There's one based on neutrinos, okay, that George was actually a part of in the neutrino group at Virginia Tech. And there's one based on A that I have to look up for you about where the quote is. Yeah, it was based on the Sorkin parameterization and just sort of putting a bound on that Sorkin parameter for triple interference.
Okay, thanks.
Okay.
We have another question here.
There's been quite a bit of work on the Ricci flow around these Fabini-Studi metrics. Would this be relevant at all? I mean, I don't see that there's any Ricci flow here, but that could be interesting.
I don't know. I don't know the answer to that.
Yeah, I could
Yep.
tell you about some of this work.
Okay, yeah, I'd like to hear that. Yeah. Thanks.
Okay, any other question? Ed?
So there's quantum mechanics makes 2 sorts of predictions. One is if you have an observable, it has eigenvalues, and if the state is an eigenvector, then the outcome is definitely the corresponding eigenvalue if you measure it, right? And that's compatible with the Born rule in the sense that the expectation value of an operator in a state is equal to the eigenvalue of the average value operator on n copies of that state in the limit that n goes to infinity.
Yes.
If you, in the sense that that product state becomes infinitely close to an eigenvector of the average value operator. Yes. So all I'm trying to say is there's a kind of compatibility in standard quantum mechanics between the eigenvalue rule of quantum mechanics and the probability interpretation. So I'm wondering if in the kind of modification that you're contemplating for the probability structure of quantum mechanics, would you still maintain a compatibility with the eigenvalue postulate?
So yes, right? But the compatibility may be, or the actual eigenvalue may be experiment dependent. Okay, so we have a probability rule here, right? That says that the actual outcome of the probability rule, and it's a probability, right? So you can take averages and stuff just as you would for usual probability, right? But that the probability rule is contextual to the experiment that you're doing, right? So that I would argue is the difference. Does that make sense? And that's a non-trivial difference, right? Because if you do a different experiment, all right, then the question is, do you get the same averages, right, that you should be able to classically compare, right? So it's not really, for me, it's not a comparison of that aspect. It's saying, as I get average values that should be classical, what does it mean if different observers see different values of those classical parameters? Did I get your question right, or did I take it? Yeah.
It sounds like you might be saying that unlike in standard quantum mechanics, an observable in your theory wouldn't just be characterized by some fixed
it doesn't depend.
It
doesn't depend just on the density matrix. All right, so we think of observables as just being trace of row O, right? It's expectation values. The way that usually is that the density matrix here, in the language of Chetsov information, the density matrix counts as a sufficient statistic to fully describe the probability distribution given the operator, right? That's it. Here, what we're saying is that whatever you replace the density matrix with has to be a function of the experimental context on which you're doing.
So, Pat, are you also replacing what is normally meant by an observable in the theory, or are you only changing what's meant by the state?
We're changing what is meant by, no, observables will still be operators, right? Acting on states of some sort, right? And possibly the experimental context, okay? So we're not changing that, but we are changing then how we would calculate averages of those, so overall expectation values of the observables. Okay. Yeah, okay, I'm not sure, yeah.
Okay, well, one last question.
All right. Thank you.
You're gonna say, so-and-so tried this back in 1922.
Part of it is that, I'm very sympathetic to this idea of like gravitating quantum mechanics instead of quantizing gravity. And I wonder, but like I wonder what the way I naively think about it, how that relates to what you're doing, right? So I also like this quote by Scott Aronson about like, the quantum mechanics is an operating system on which we write like different applications. And you could make the same story about like relativity, like, special relativity is like a new operating system. What we need to do now, you can write down any kind of theory, but you'd better make sure that you only introduce Lorentz invariant quantities. All that operating system is encoded in the geometry of Minkowski spacetime. Okay. Similarly, all the quantum mechanics, like the operating system, is encoded in the geometry of Hilbert space, right? So here's the bit about like somebody did this before, von Neumann in 1927, in like his the second paper of his famous trilogy, Wahrscheinlichkeitstheoretische Aufbau der Quantenmechanik, like quantum, like probability theoretic building up of quantum mechanics, right? He showed that with this early derivation of the Born rule, like that basically, like the Hilbert space formalism locks you into the Born rule. That was then later sort of perverted to this no hidden variable theorem, and Bout and all this. There's a long literature about this, but that was the idea, and he was actually like motivated by von Mises, who is like the arch frequentist, right? And like a lot of people in foundation quantum mechanics, they think frequentist is all wrong and all this, but he was a frequentist, and so so one way to then think. So basically, what von Neumann is saying, like Hilbert space is giving you this new way of doing probability theory. And what I find striking is what I didn't know until like a few years ago, that Hilbert space is also like the standard tool in modern probability theory, right? And so if you read people like in this information theoretic literature, they're saying like basically quantum mechanics is just a more general probability theory that is just, like standard probability is a special cases. I'm almost there.
Okay.
So so just as you went from Minkowski spacetime to curved spacetimes, like, is it fair to say that if you think about gravitating quantum mechanics, that you're trying to change the structure of Hilbert space?
In a sense, yes. Yeah. So, and we change the structure of how we actually map states, right, to physical outcomes. Yes, without question. Like this is a non-trivial. So to change Hilbert space, right? Let's think of, remember I said before that like the block sphere is CP1, right? Well, if this is actually true, right, then it's not the Born rule, which means that the invariance of the Born rule is unitaries, right? Well, unitaries don't necessarily satisfy that, which means that the projectivization of the usual C3 that you have for Hilbert space, you're not modding out by U1, you're modding out by something else. So that's definitely changing a lot about the structure of Hilbert space there, without question. I hate it, but at the same time, I really like the idea that things should come from somewhere, right? And we need to test with realistic experiments. So I'm caught between a rock and a hard place.
Okay, one last question.
So I think you said at some point you need the frequentist approach to connect to experiment, and I didn't understand that statement. I mean, why can I use a Bayesian, a probability kind of thing to connect to experiment?
So what I'm saying is that to use if I use a Bayesian approach, right, then basically I'm checking to see whether or not my theory that I have, quantum mechanics, right, satisfies a set of probabilities with respect to some prior assumptions, right? And I'm trying here to not have any priors. Okay, I'm trying to say, there's no other logical underpinnings that I have here, right, other than experiment, where I could tell you that this outcome is right or this one. So that's why I'm striking the frequency. If you chose to do relational quantum mechanics or Bayesian quantum mechanics, I'm not saying anything about those, right? So those may be ways out as well. Does that help?
Yeah, I mean, I guess the whole point, I guess, of Bayesian analysis is exactly that you always have some priors, and you're trying to find some posterior. So you could try to, perhaps you could try to reformulate everything and say, okay, no, actually, I'm going to take a Bayesian interpretation of probability and try to build a framework on that.
Yes, I mean, there are theorems, von Mises has one, right, that actually relate the frequentist approach and to the Bayesian limits and stuff. So they do have to coincide in usual Bayesian analysis. So there is, in principle, a way that you can translate this to Bayesian, to cubism, basically, but we haven't tried.
Okay, I think we can call off the day. And thanks again to the speaker, and see you tomorrow.